Hello everyone, welcome to Dynamics 2. My name is Dr. Zahurullah. I'm a lecturer in the School of Mechanical and Aerospace Engineering. Now, in the next 4 weeks, we will discuss mainly two topics. So, the first topic that we will discuss in the first semester is about the torque diagram and speed fluctuation, and then the second topic that we will discuss in the second semester in the first 2 weeks is about the rotating balancing. So in addition to the lectures, we will also have tutorials. You have tutorial 4, which is for the torque diagram and speed fluctuation, and then you have tutorial 5, which is for the rotating balancing. We will also have a class test in week 4 in the tutorial class. So it will be 1 hour test, an open book test, and you will have 1 hour time. But to be eligible for the class test, you will need to submit the at least one of the tutorial. So that is the 50% of the tutorial that you will need to submit here. And this test will contribute 15% to your marks. Okay, so in the today lecture, we will mainly concentrate on the torque diagram and speed fluctuation. So as you can see here, that the torque diagram is the output from a 4-stroke or 2-stroke engine. So just to keep everything in context, we will just revise the idea of 4-stroke and 2-stroke engines. Then we will discuss about the torque diagram for a single cylinder, and then because the torque diagram is fluctuate over the crankshaft angle, so we will also then discuss about how the crankshaft speed will change over time. And then another important concept is the design of flywheel. So flywheel, as you can see in this figure here, so this is the flywheel. So we will discuss about the design of flywheel so that we limit the speed fluctuation in the crankshaft. And then we will discuss about the torque diagram for a multiple cylinder engine. As you can see in this case here, so you have this is cylinder 1, cylinder 2, cylinder 3, and cylinder 4. So if you have this sort of situation, then how you will construct the torque diagram for this specific case. And finally, we will discuss some numerical examples so that we can apply the theory that you learn in these topics. For a 4-stroke engine is shown in this figure here. So these are the main components of a 4-stroke engine. So as you can see, you have a intake valve, you have an exhaust valve, you have a spark plug here, and this is the combustion chamber. We also have a piston which is connected to the crankshaft using this connecting rod. So in the 4-stroke engine, you need a 4-stroke to complete the whole cycle. So in the first stroke, which is the intake stroke, in the intake stroke, the piston will move from this location, which is the what we call is the TDC, or the top dead center, to the BDC, or the bottom dead center. So the piston will move from the TDC to the BDC. TDC is the topmost position of the piston, and BDC is the bottom most position of the piston. Now during this intake stroke, you will open the intake valve, and this will suck the air fuel mixture into the combustion chamber due to the vacuum which will create due to this movement of the piston. And again, you can see that when the piston move from the TDC to the BDC, this will rotate the crankshaft through 180 degrees or pi radians. Now in the next stroke, which is the compression stroke, so in the compression stroke, you are compressing the air fuel mixture, and you will close both valve. In the next stroke, which is the power stroke, so again both valves are closed and you are just igniting the air fuel mixture, and this will force the piston to move in the downward direction here, from the TDC to the BDC. And this is the power stroke, and in the final stroke, which is the exhaust stroke, so in the exhaust stroke, again the piston will move in the upward direction here, and this will and during this stroke you will open the exhaust valve, and this will force the air fuel mixture through the exhaust port. So these are the main four strokes in a four-stroke engine, and in each stroke the piston is moving from the bottom dead center to the top dead center, or vice versa. And in each stroke the crankshaft is rotating through 180 degrees. So this means that for the whole cycle you need 720 degrees or 4-5 radians. Now the next engine is the two-stroke engine. So in the two-stroke engine you need only two-stroke to complete the full cycle. So we will call these upstroke and downstroke. So as you can see in the first stroke, when the piston is moving in the upward direction here, so this is the direction of the movement of the piston. So what you will have is you have you will open the valve here, because the piston is moving in the upward direction, so it will create a vacuum here which will open the valve, and it will suck the air fuel mixture into the crankcase here, and you are covering the transport port, and obviously there will be ignition in the combustion chamber. So in the next stroke, which is the piston will move in the downward direction. So when the piston will move in the downward direction, it will forces the air fuel mixture in the crankcase to move to the combustion chamber through the port here. So the air fuel mixture will go through this direction into the combustion chamber, and this will the burn fuel will be pushed out by these compressed air fuel mixture from the combustion chamber. And as you can see, during one stroke the piston is again moving from the TDC to the BDC, or from the BDC to the TDC, and during the one stroke the crankshaft is rotating through 180 degrees. So for the full cycle of a two-stroke engine you need 360 degrees or 2 pi radians. Now about the torque diagram, as you can see in this figure here, that this is the typical diagram for a four-stroke engine. So on the y-axis we have a torque, and on the x-axis we have the crank angle in radians or in degrees. Now as we discussed previously, the torque output from an engine fluctuate over the engine cycle, and this is due to the variation in cylinder pressure and inertia forces. Now the exact shape of this diagram will obviously depend on different parameters, including the size of the engine and also the forces inside the combustion chambers. Now as you can see from this point to this point here, it is the intake stroke. So during the intake stroke the piston is moving in the downward direction, and this will create a vacuum here, and it will suck the air fuel mixture into the combustion chamber. So because you are working on the system here, so this means that the torque output from the engine is negative, so that's why you get this negative area here. But because of the of the inertia of the piston and the pressure from the of the gases in the combustion chamber, you will get some sort of positive torque from the engine here. So we will get this positive area here. Now from this point to this point here, which is the from this point to this point here, which is the compression stroke. So during the compression stroke, you are again working on the system, and therefore the torque is negative here. And if you see the way the torque is changing, that initially the the torque is smaller as compared to when you are approaching the top dead center, because it's getting harder and harder to compress the air fuel mixture here. Now from this point to this point here, which is the power stroke. So during the power stroke, obviously you are getting a positive torque. So this is the positive area here. And then the same case is in the exhaust stroke. So in the exhaust stroke, obviously you are working on the system to remove the gases from the combustion chamber. So you will get some negative torque, so means you are working on the system, and due to the inertia of the piston, you are getting some positive torque here. So this is the typical diagram for a four-stroke engine. Okay, now another important parameter that you will always need to find in the numerical example is the mean torque. So the mean torque is the average torque from a torque diagram. So this is the same torque diagram that you saw on the previous slide, and here now we want to calculate the mean torque or the mean output torque from this cycle. So the equation that we will be using for this case is given here. So the mean torque is equal to the net, which is the positive area of the diagram, and divided by the base length. Now for this specific case, which is a four-stroke engine, so in this case you can see that you have different areas here. So the first area here, which is the A1 in the black color, this is the negative area. Then the area which is from this point to this point was a positive area, and then you have a negative area here, A3, and then the A4 is the positive area. Again, A5 is the negative area, and A6 is the positive area. So if you want to calculate the mean torque, you will just add all these areas together, but making sure that you will subtract the negative areas and add the positive areas. So in this case, you will have the minus A1 plus A2, then you have minus A3 because it's a negative area. A4 is positive area, so we will add A4. A5 is negative area, so minus A5, and then plus A6, and then we will divide by the base length. So the base length mean that we will divide it by the 4 phi radian here. So if you calculate all these areas and divide it by the base length, what you will get, that you will get the mean torque. And as you can see in this figure here, that the mean torque is always positive, because from the engine you always need a positive torque to for example run your car. So in this case, the mean torque is this green line here. Okay, now we can talk about the speed fluctuation. As you can see that the torque is fluctuating, it's not constant, but we can assume here that the mean torque is approximately equal to the external load or the torque required at the crank. Okay, so we will assume here that the mean torque is the torque that you required to run your car, for example, from the engine. But the actual torque from your engine is not constant. It's changing over cycle. So what will happen that is the torque produced varies between being greater than and less than the required torque. So the crank speed tend to fluctuate. So as you can see in this case that from this point to this point here, the the actual torque is less than the required torque. Now from this point to this point, the actual torque is higher than the required torque, and similarly from this point to this point, again uh, the the actual torque is less than the required torque. Uh, so what will happen is that when the output torque is lower than the required torque, the engine begin to decelerate, and because we have insufficient torque to maintain the speed. But on the other hand, when the output torque is greater than the required torque, so then the engine began to accelerate because we have excess torque, which is causes acceleration of the engine components. Now, if you want to draw now how the speed of the crankshaft will change over the cycle of the engine, so you can see this in this figure here. So obviously this is our mean torque, the green line, and if you draw the instantaneous speed here of the crankshaft, so obviously the crankshaft is rotating. So here we are talking about the angular velocity. So angular velocity omega 1 is the maximum angular velocity of the crankshaft, and omega 2 is the minimum angular velocity of the crankshaft. And obviously this is the crank angle here. Okay, so now as you can see, the torque is changing with respect to angle here. It is not constant. So first we will do is that we will mark all the points where the torque diagram is crossing the mean torque line. So we have these point A, B, C, D, E, and F and G. So we have all these points now. So you can see that the area between A and B is a negative area. From B to C, it's a positive area here. From C to D, it's a negative area. And similarly, from D to E, it's the positive area. From E to F, it's a negative area. And from F to G, it's a positive area here. Okay, now what is happening from A to B? So from A to B, because the actual required torque from the engine is the green line here, but the actual torque is changing like this. So this means that you have a negative area here. So the actual torque is less than the required torque. So this means that the piston, the crankshaft will decelerate. So this means that the velocity of the crankshaft is decreasing here. So it's decreasing as you can see here. Now from B to C, the actual torque is higher than the required torque. So you will see some sort of acceleration of the crankshaft. So this means that you are getting some acceleration. So the velocity of the crankshaft is increasing here. And now from C to D, there is a negative area. So there is a deceleration here. And from D to E, there is again a positive area. So you will get acceleration here. So the velocity is increasing from omega 2 to omega 1 here. And finally from E to F, again a negative area. So you are getting the velocity is decreasing here. And then from F to G, you will again get some sort of acceleration here. Now the as you can see, the speed of the crankshaft is again not constant. It's changing between this omega 1 and omega 2. Omega 1 is the maximum speed of the crankshaft. Omega 2 is the minimum speed of the crankshaft. But the mean speed of the crankshaft, which is this omega here, is, you can calculate that omega is equal to omega 1 plus omega 2 divided by 2. So if you do this, you will get the mean speed of the crankshaft here. So you can see on this slide that we will then talk about the design of the flywheel to reduce the speed fluctuation. Now the speed fluctuation can be controlled by incorporating a flywheel. So flywheel uh, is um, is a device, a mechanical device which store energy when it is not required, and will supply energy when it is required by the engine. Uh, so as again you can see in this figure here that the maximum speed fluctuation, which is in this case here, so the speed here is increasing from omega uh, 2 to omega 1, and this is the maximum energy fluctuation, so you can say that it is delta E. So this energy is you can relate this to this maximum change in the speed. So you can say that the maximum speed fluctuation can be related to the biggest energy fluctuation which occur during the cycle. Uh, okay, so now as you can see in this slide here, that the work done by a variable torque, and hence energy is available to the engine. So if you want to calculate the energy produced by this torque during the cycle, so the equation to calculate the energy from the torque is this equation here. So it is t, and so it's the integral of t, or of the torque with respect to angle here, and this is equivalent to a case which you are familiar with, is that if you apply force on a body and the body displaced through a distance dx, so we know that the work or energy is equal to the integral of force with respect to dx. Okay, so this is equivalent to this case here. So this is the linear motion, and this is the angular motion. So in the linear motion we have force, here we have torque, here we have dx, which is the displacement, and here we have the angular displacement. So this is how you write the equation for the energy from this torque, or in other words, if you find out the area under the curve from the torque diagram, which is the integral of t with respect to d theta, you will get the energy. Okay, now the fluctuation in energy is available to the engine, that is to accelerate or decelerate the rotating parts. As you can see in this figure here, that the energy from the engine is again not constant, it's fluctuating. So from A to B, you can see that there is a negative energy, then there is a positive energy. So this area under the curve is what we call is the energy. Now, simple equation is that E is the energy at a specific location. For example, if you want to calculate the energy at point D, so it will be the mean energy, and then you will write that plus minus is the excess or deficient energy. and you can also call it delta E. So delta E is the this energy fluctuation, and that is the area above is positive and area below is negative. That is above the mean torque line between theta n and theta n plus 2. So in this case, for example, if you are interested to calculate uh, the energy between these 2 points, so if this is our angle is theta n and this angle is theta n plus 1, so theta n is, for example, a specific angle, and theta n plus 1 is again a specific angle at another location, and you are interested to calculate the energy fluctuation between these 2 points. So this is what we call is the delta E, or the energy, and which will be the integral from theta n to theta n plus 1. And in this specific case, what we will do is that we will just uh, calculate this integral, and here we are subtracting t mean. uh, we are subtracting the t mean from the torque, because mean torque is our reference torque here. And if you integrate this with respect to theta, so this will provide you with the energy fluctuation. As you can see in this case, that the fluctuation in the work done by the torque is converted into a fluctuation in the kinetic energy of the engine. So F delta E is maximum energy fluctuation occurring over the cycle. Then the speed changes from the lowest value omega 2 to the maximum value omega 1. So this fact is really important, and you will often use this during the numerical examples, that you have, for example, here the maximum energy fluctuation occurring here is from theta n to theta n plus 1, so from D to E. And this is changing the speed of the crankshaft from the lowest value, which is omega 2, to the highest value, which is omega 1. And again, this energy is changing the kinetic energy of the crankshaft. Okay, so if you consider the crankshaft, what will happen is the delta E is changing the kinetic energy of the crankshaft. Okay, so if you consider the final kinetic energy with the speed omega 1, so which will be half I omega square, omega 1 square, and the lowest energy will be half I omega 2 square. And again, this is equivalent to the linear case is half. uh, so in the linear case, the kinetic energy is equal to half mv square. So in the circular motion, or in the angular motion, mass is inertia, and here the moment of inertia is I. Here we have the speed is velocity here, and here we have the angular velocity, which is omega. So this is the kinetic energy uh, uh, at speed, or angular velocity omega 1, and this is the energy at angular velocity omega 2. So this energy fluctuation, or the maximum energy fluctuation, will change the kinetic energy of the crankshaft uh, its speed omega 1 to kinetic energy its speed omega 2. And here this I is uh, is the uh, is the moment of inertia of crankshaft, and plus flywheel. Yep. Okay, so as you seen earlier, that we have this equation here, that delta E is equal to half I omega 1 square and minus half I omega 2 square. So now we can write this equation because half and I is common. So we can write this is omega 1 square minus omega 2 square. Now we can simplify this equation a little bit more. So what we will write is that delta E, which is equal to so you can write this omega 1 plus omega 2 and then omega 1 minus omega 2, or we can write this in this form here. So omega 1 plus omega 2, and you can write the 2 here, and then omega 1 minus omega 2 here. Now in this case, this thing here is our omega 1 plus omega 2 divided by 2 is the mean speed, which we can represent by omega. So this will become I omega, and then we will have omega 1 minus omega 2. So this means that delta E becomes something I omega and omega 1 minus omega 2. Now now this is the equation uh, for the maximum energy fluctuation, which is equal to I, which is the moment of inertia of the crankshaft and flywheel. Omega is the mean speed of the crankshaft, and omega 1 is the maximum speed, and omega 2 is the minimum speed of the crankshaft. Now we can just rewrite this equation in a little bit different form. So what we will do that we will multiply this equation with the omega. So this will become omega square, and we will divide the same equation by omega. So it will become like this. We are writing this equation in this form because it's a little bit convenient to use this in the numerical examples. So this will be our final equation, and this is really an important equation and will be used in most of the numerical examples. Now this term here in the bracket here, which is omega 1 minus omega 2 divided by omega, is what we call is the so omega 1 minus omega 2 divided by omega is what we call is the fractional speed fluctuation. So this omega 1 minus omega 2 divided by omega is the fractional speed fluctuation. And again, as you can see here, that if you can find out the speed fluctuation in energy about the mean from the torque diagram, so if you can calculate this delta E, we can identify the inertia required. So we can calculate the I here, which is the inertia of the flywheel and crankshaft, to limit the speed fluctuation within a certain percentage of the mean speed, and we can achieve this by this inertia by adding a flywheel to the crankshaft. So the main idea is that if you can calculate delta E from the torque diagram, and then you can control this speed fluctuation of the crankshaft by incorporating some sort of inertia in the system. Okay, so now again we will discuss about the design of the flywheel while considering the hoop stresses here. So if you are familiar with the idea of cylinders, that if you consider a cylinder here, a thick wall cylinder or thin wall cylinder, so in cylinder we have different type of stresses. So one stress is in the so one stress is in this direction here, which is what we call is the sigma h, or the hoop stress or circumferential stress or tangential stress. One stress is in this direction here, which is what we call is the radial stress, and one stress is in this direction here, which is what we call is uh, the longitudinal stress. So the same idea we can apply to the flywheel. So as you can see in these figures here, this is how the flywheel look like in practical applications. The flywheel you can consider is a thin rotating ring here, and all the mass of the flywheel is locating somewhere in this section here, or you can see in this section here, which is what we call is the rim of the flywheel. And the mass between the rim of the flywheel and the center of the flywheel is that we can ignore in this specific case because it will be small. So as you can see in this case, uh, that the rim of the flywheel require a centripetal force to maintain circular motion. So in this case, because the flywheel is rotating here at very high RPM, and the centripetal force that will be applied to the flywheel is can be written by this equation here. So m is the mass of the flywheel, and omega square r is the centripetal acceleration. So m omega square r is what we call is the centripetal force. And here in this case, m is the mass of the rim, omega is the crankshaft speed, and r is the radius of the center of the flywheel annulus. So in this case, because we will consider that the that this rim of the flywheel is again not very thick here, so we will consider a thin ring here, and therefore this mean we will consider this r is the mean radius here. So omega square r and then m. Okay, so as you can see uh, in this case now, that if you consider a small element of so if you consider this small element here, so this will be again a small section of the flywheel. So in this case, this angle is, if you consider, is a delta theta, which is a very small angle here, and the centripetal force in this case is going to be in this direction here. So the centripetal force will be in this direction, and the forces which is due to the hoop stress, which is the main stress which can cause failure in the flywheel. And we can write this by using this equation here. So sigma h, which is the hoop stress, and multiplied with the cross section area. So if you multiply the cross section area of the flywheel, of the rim of the flywheel, which is going to be this area here. So if you take this area, and if you multiply this with the hoop stress, which is acting on this cross section area of the flywheel, so then you will get this hoop force, or you can call it F. And another thing is that if this angle is delta theta, so then this angle will be half of this delta theta, and if this angle is delta theta by 2, so this angle is again delta theta by 2. And so in this case, we can split this force into two components. This will be the horizontal force, and this will be the vertical force. Similarly, this force is again sigma h times a, and again this can be split into two components. So one is the one is the F in the vertical direction and one is in the horizontal direction. And again, this angle here will be delta theta divided by 2. Okay, so in this case, what do you have is that if you want to calculate the mass of the flywheel initially, so the mass is obviously equal to density time volume of the rim. So in this case, you can write the density, which is rho in this case, and to calculate uh, the volume of this rim. So for this small section here, so what we will do that we will take the cross section area and then we will multiply uh, with the this distance here, which is r d theta. So this means that if you take this circular arc, which is r d theta, and you multiply this with the cross section area, so you get the volume of this specific element here, and then you multiply this with the density, so uh, you get the mass of the this small section of the flywheel. Now for this specific small section, we can also calculate the centripetal force here. So the centripetal force is just mass times and omega square r. So if you take this mass, which is we know now the value of the mass, so r d theta, and into omega square r. So this is the value of the centripetal force. Okay, now again, if you can see the hoop stress created in the ring is sigma h, and the forces F acting on the cross section is again this sigma HA. So as we know that sigma h, which is the hoop stress, and if you multiply this with the cross section area of this rim of the flywheel, so then we will have this thing here. Now again, as you can now try to apply the equilibrium equations to this figure here. And again, this force here that you can see is the centripetal force, so which is in this case is uh, density times A, which is this force here. So you can write it like this. So AR delta theta into omega square r. So now if we resolve the forces in the y direction, so as you can see in this figure that this force, which is FH, is in the negative x direction, and this force, which is this force here, is in the positive x direction. So these two forces will cancel each other, and there is no other force in the x direction. So in the x direction there is zero force. The only forces that we can see here is only in the y direction. So if we resolve this forces in the y direction by using this Newton's second law, so what we can write here is that uh, we have two forces which is in the vertical direction. So Fv here, and this is Fv here. So this Fv means the vertical component of this force here, and then we have this centripetal force, which is also acting in the y direction. So now if we take this the Fv, so it is the sigma h times A, and then you need to multiply this with the sine of delta theta divided by 2. Okay, and you will multiply this with the 2 because we have two forces. So one force is this and one force is on the other side, and this will be equal to this force here. So which is this MAY, which is the centripetal force here. So what you will have, the density times A and R, delta theta and omega square R. Now there is another important concept in mathematics, that if angle is very small, then what we can write is that sine of theta is equal to theta, and cos of theta is equal to 1 if the angle is very small. So in this case, because this angle delta theta is very small angle, so therefore we can replace this sine delta theta by 2 by just delta theta by 2. So what we will have here is that 2 sigma h a delta theta by 2, and on the right hand side again we have this term here. Okay, so now as you can see in this equation here, what we have, that we have 2 here and 2 here, so these can cancel with each other. We have cross section area on this side and cross section area on this side, so which we can cancel with each other. Again you have delta theta here and delta theta here, so which we can cancel with each other. So finally what we get from this equation is that on the left hand side the only thing left is this sigma h here. So sigma h become equal to, on the right hand side what we have is that density rho, and then you have omega square, and you have one r here and one r here, so you will have r square. So in case of the flywheel, we have this again a very important equation here. This is again a very important equation here, and then you will be often used in most of the numerical example, that the hoop stress in the flywheel is equal to density times omega square, which is the mean speed of the crankshaft, and r is the mean radius of the rim of the flywheel.